Welcome to our webinar, in which we will introduce our new large field of view Raman Spectroscopy kit. We'll start off by introducing various applications of Raman Spectroscopy. What this technique essentially does is to provide a chemical fingerprint of your sample. Having this chemical fingerprint available is beneficial in many different fields. It provides a quick and easy way to quantify the composition of known or unknown chemical mixtures. This can, for example, be used to identify illegal or dangerous substances during police patrols or in sensitive areas such as airports. You can also use the information provided by the chemical fingerprint for quality inspection in a number of different products. Pharmaceuticals, food, and many more items can be screened for contaminants. You can also verify that certain desired chemical compositions are reached. This can either be implemented in real time during or in quality control at the end of your production process. Raman Spectroscopy can also be a useful tool in monitoring chemical processes at production sites and facilities in real time without having to take samples to a laboratory. One of the biggest advantages is that Raman Spectroscopy requires no sample preparation, so it is easy to use and may even be implemented for continuous live monitoring. The technique is non-destructive and non-invasive. It does not even require you to touch your sample. Later, we are going to demonstrate that you can even analyze the contents of a sample through transparent packaging like glass or polymer. Other optical methods that can provide similar information like direct IR or near IR absorption suffer from water interference. Raman spectroscopy is not susceptible to that, which makes it significantly more versatile in its uses. The typical acquisition time is fast. You can get a spectrum after a few seconds. A typical Raman spectroscopy setup is shown here on the right. It begins with an excitation laser, which is directed onto the sample. The laser light gets scattered up the sample and collected with collimation optics. Then it is directed onto the entrance slit of the spectrograph. Here, the different wavelength components of the light are spatially separated by a dispersive element like a grating. Finally, the light is detected by the sensor. What you can observe when doing this analysis is that the scattered light has different wavelengths than the initial excitation beam. To understand this and to see what information you can get from this change in wavelength, let's have a look at the physics behind the Raman effect. First, the sample molecules are excited from the ground state to a virtual state. The lifetime of the state is very short, and the molecules will relax fairly quickly. Most immediately go back to the ground state and scatter light of the same wavelength as the excitation laser. But some relax to excited vibrational states and emit light at a longer wavelength. A longer wavelength corresponds to lower energy. This difference is called the Raman shift and directly equals the energy of a vibrational mode in the molecule. These vibrations are very specific to each of the chemical components in your sample. This is especially true for the lower wave number spectral region, also referred to as fingerprint region. Here you'll find many vibrations of the whole molecular framework. You can see an example here to the right. The higher wave number spectral region mostly contains vibrations of terminal atoms, such as carbon-hydrogen pairs. The information provided by these vibrations as a whole allows for a detailed analysis of the chemical composition of your sample. To get useful information from Raman spectra, a spectral resolution of 5 to 20 cm to the -1 is usually necessary. In conventional spectrographs, this is achieved by using a small aperture slit. The more narrow the slit, the better the spectral resolution. Typically, extremely small dimensions with less than 25 microns width and about 1 mm height are chosen to reach the needed resolution. The trade-off for this is that a lot of light intensity is lost at the small aperture. So conventional setups need to compensate for this in several ways. They typically use rather expensive cooled sensors and long exposure times for averaging to generate their spectra. In addition, they also need to increase the light intensity scattered from the sample by using a high-power laser beam focused onto a very small spot. The typical spot diameter is only a few microns. This results in a high laser power density of the excitation beam and generates a lot of Raman scattering from your sample. The drawback is that you can only measure very small spots of your sample at a time, and the field of view is therefore rather limited. In addition, delicate samples might be damaged by the highly focused laser beam. For the most part, the design of our spectrograph is very similar to a conventional one. But instead of the slit, we have a significantly larger coded aperture at the input of our spectrograph. It is 2.3 by 3.2 millimeters. You can see the size difference between our coded aperture and a conventional slit aperture illustrated here. Normally, a large aperture would decrease the spectral resolution to a point where it is difficult to get useful information out of the Raman spectra. We solved this issue by using a coded mask inside the aperture. The pattern you see here is not random. It is actually a mathematical pattern called Hadamard mask, encoded by the succession of light and dark areas. So, by using the mask, we can recover the Raman spectrum with a spectral resolution between 7.8 and 9.7 cm to the -1 by deconvoluting the 2D images acquired by the 2D camera sensor. The larger aperture allows for a vastly increased light throughput to the sensor. This enables us to use significantly more cost-effective sensors, such as our Kirillux, a room temperature CMOS camera. We are also able to use a laser beam for excitation that is not focused. So we can illuminate a 2 square millimeters area, giving us a large field of view. You can see a comparison between our field of view and a conventional one here. This makes it a lot easier to analyze inhomogeneous samples like powders or pills, because we can perform integrated averaging over a large area, instead of having to successively scan a lot of small points. This is an easy way to get the full picture of a sample's composition without many time-consuming measurements. In addition, the lower power density of our large excitation beam preserves delicate samples better than a small, highly focused beam would. The focus beams can sometimes even burn or ignite particularly dark or sensitive matter. Here we have a picture of our new Raman spectrograph with the coded aperture at the input. The system comes wavelength calibrated and amplitude corrected, allowing for a direct comparison of the recorded spectra with spectral databases. It can be used with a 785 nanometer laser to cover the spectral range where many chemical compounds have their fingerprint vibrations. Optionally, with a 680 nanometer laser, a different wave number range can be reached, where typically vibrations of terminal atoms can be found. We offer suitable lasers to be used with the spectrograph, but of course you can use your own lasers if they have the correct specifications. Here we have all the important specifications for our Raman Spectrograph RSB1 at a glance. Our input aperture has the size of 2.3 by 3.2 mm, and the spectrograph has a numerical aperture of 0.22. The spectral resolution is guaranteed between 7.8 and 9.7 cm to the -1, or lower than 0.65 nanometers. It can be used with a 785 nanometer laser to cover the wave number range from 500 to 1800 cm to the -1, where most fingerprint vibrations are located. Optionally, a 680 nanometer laser can be used to cover the high frequency range from 2000 to 3600 cm to the -1, where mostly vibrations of terminal atoms are located. At 10 seconds measurement time, the setup typically delivers a signal-to-noise ratio of about 700, slightly dependent on the sample. Our amplitude is corrected for making the spectra directly comparable to available databases. The correction follows the NIST standard SRM2241. The Raman measurement software is integrated into our standard OSIS software, which can be downloaded free of charge from the Thorlabs website. Here we show the frontends, which are specifically designed to be used with our spectrograph. Different versions are available for liquid and solid samples. Both use a fiber-coupled laser input and come with calibration standards for your laser wavelength. All necessary optics are included and pre-aligned, so you can get started instantly. All you need to do to start recording Raman spectra is attach a front end to the spectrograph and then attach a suitable fiber-coupled laser to the front end. The first front end is our reflective RSB1 for solid samples like powders. The samples can be placed on the table shown here. The second front end, RSB1, is designed around our cuvette holder and holds liquid samples. Both spectrograph and front ends are compatible with standard Thorlabs optomechanics, giving opportunity for easy modification and customization. Therefore, you can modify the parts to fit your individual needs. Let's summarize the benefits of our new Raman Spectroscopy kit. Because of our unique feature, the coded aperture, we have a large light throughput, while maintaining the high spectral resolution which we need for Raman spectroscopy. Our large beam diameter up the sample makes it a lot easier to analyze inhomogeneous samples, like powders, because we can perform integrated averaging over a large area instead of having to scan a lot of small points. The lower power density also helps when analyzing delicate samples. The typical measurement time is only a few seconds. Our line of accessories helps you to get started instantly with your Raman measurements. Of course, you can always build your own setup, as the kit is compatible with standard Thorlabs optomechanics. It allows for a lot of customization on your end to adapt the measurement setup to your specific needs. In this demonstration, we will show some uses of our new Thorlabs Raman Spectroscopy kit. You can see the spectrograph and the camera here to the right, our reflective front end for solid samples in the center, and a fiber-coupled 785 nanometer laser to the left. The 250 mW wavelength stabilized laser beam is collimated here and then hits the sample holder from above. The laser is not part of the Raman kit, but Thorlabs can provide you with a suitable solution. Alternatively, any laser with appropriate specifications can be used. On the screen, you now see the included Thorlabs OSIS software for spectrum acquisition and processing. The green indicator lamp marked with C shows that the system is properly connected. Also, the wavelength dispersion calibration included with the system is correctly loaded. The second lamp would indicate a sensor saturation, leading to incorrect peak heights. The third lamp shows whether a dark image has been acquired. In the settings menu, we can choose some reasonable acquisition parameters. An exposure time of 10 seconds, an analog gain of 0 dB, and a black level of 40 are a good choice for many samples. If the sensor is saturated, this indicator lamp will highlight that the chosen parameters need to be adjusted. When you have identified good acquisition settings for your sample, we recommend acquiring a dark image. This needs to be done at the same settings which are used for the subsequent measurements. Now the dark image indicator lamp turns green, and the dark image gets subtracted from the sample images. This effectively reduces the impact of sensor noise on the reconstructed Raman spectra. Note that the excitation laser wavelength was previously determined and entered to the software here. This is necessary to ensure exact spectral positions in inverse centimeter scale, which is required if you wish to compare your spectra to reference databases. We supply calibration standards and a calibration routine with the kits for this purpose. To guarantee correct relative peak heights, the Thorlabs Raman kit comes with a NIST amplitude correction that is enabled per default. To disable amplitude correction, you can check the mark here. For proper comparison to reference or database spectra, we now want to re-enable amplitude correction. Now we are ready to perform Raman spectroscopy on the samples. First, we will check these solids. We have two different plastic tubes and aspirin pills, both with and without their packaging. The first one we place on our sample holder is a plastic tube made from Teflon. We start our measurements with an exposure time of 10 seconds. This is sufficient to achieve a good spectrum of the material. In the black trace here, we can already identify several distinct peaks, like this one, or these three over here. Now we can load a reference spectrum. If we scale the reference spectrum shown here in red for comparison, we can see a perfect match of the Raman lines. The second tube is made of polyvinyl chloride, or in short PVC. Again, we acquire the spectrum with an exposure time of 10 seconds. The recorded spectrum will appear in black. Now we add the reference spectrum of pure PVC in red. If we compare both spectra, we can clearly assign many peaks to PVC, like these here, or this one over here. But obviously there are some additional peaks, which are not accounted for by the PVC itself, like this one or these over here. This is to be expected, since pure PVC is a hard material, whereas the tubes is flexible. This is usually achieved by adding plasticizers to the polymer. To explain the additional peaks, we load a reference spectrum of one of the most common plasticizers, DEPH. If we now compare the reference spectrum in blue and our measured spectrum in black, we see that many peaks that we couldn't assign before are caused by the presence of DEPH in the PVC tube. We see that Raman spectroscopy is a very powerful tool to detect plasticizers in polymers. This is very important because some plasticizers are considered a potential health risk. Due to its large sampling area of 1 to 2 square millimeters and depths of some millimeters, the Thorlabs Raman kit is well suited for through-packaging substance identification. As an example, we can compare the Raman response from a bare aspirin pill to the spectrum acquired through its blister. First, we insert the bare pill. Then, we record a spectrum of the bare aspirin pill with an exposure of 10 seconds again. As usual, the spectrum will appear in black. We end up with the Raman signature of acetyl salicylic acid, or ASS in short. This is the active ingredient of aspirin. Now we exchange the bare pill for the one in its blister. We record the second spectrum in a separate trace and change the color to red for clarity. Clearly, the Raman signature of the active ingredient is preserved, showing that through blister detection is possible with our setup. Now you see the Raman kit configured with the cuvette front end, RSB1. With this equipment, we are going to record spectra of pure methanol, pure ethanol, and a mixture of 10% methanol in ethanol. The first sample we are going to look at is pure methanol. We use our usual 10 seconds exposure time to record the spectrum of pure methanol. The typical Raman signature of methanol will appear in a black trace. Several distinct peaks can be found, most notably these two here, but also a smaller third one over here. Now we follow the same procedure with pure ethanol. We want to display the ethanol spectrum in a different trace, so we set the first trace to inactive and activate a new one. The acquired ethanol spectrum will appear here in red shortly. Comparing the spectra of both alcohols, we see some similarities and band overlaps, like over here, but also enough spectral differences, like here, here, and here, to tell them apart in a mixture. We expect the most meaningful difference between both alcohols at the position of the strong methanol peak, at around 1030 cm to the -1. Here, the spectral shape should change upon the presence of methanol in our mixture. We now switch to the mixture of 10% methanol in ethanol. Now we switch traces again. We use our usual 10 seconds exposure time to acquire a spectrum of the alcohol mixture. The new spectrum will appear in blue. And indeed, in the new spectrum, we see a change in the spectral shape at the exact position where we would expect it. We can make this even more visible by subtracting the spectra in the OSIS software. The different spectrum here in green clearly shows where the methanol signal is appearing in the mixture and the ethanol signal is depleted. Of course, this method could be used to detect even lower amounts of methanol than the 10% we are using here.